combustion calculation, related with the how to calculate the calorific value, and also the energy, energy, the bounded energy during the fuel combustion process, and also the energy from the evaporation. So I will explain the next task, number 8, for combustion calculation. Okay, now can you see the notes of task number 8? Is clear there? Okay, so for the task number 8, for the steam boiler combustion calculation, we will have the task to define or to determine the several properties or several values here. The first one, we need to calculate the required minimum air for the combustion. The second task, to calculate the net calorific value. And then the C is the excess ratio, or the R ratio lambda. The lambda is the excess ratio. So a week ago, I've explained about the excess ratio. This is the requirement of air for complete combustion of the boiler. So for several type of boiler, based on type of fuel, so you need a certain percentage or certain range value of lambda. For example, for natural gas, oil gas, or maybe the coal, you have a different excess ratio. So the excess air ratio is very important to have a complete combustion. So maybe you have studied in the diesel engine, you have a term of a rich mixture and lean mixture. So the air excess ratio is more or less similar with the rich mixture of air. So you have the rich percentage of air for the combustion process. But of course, you don't need the excess air too much, because the air percentage, if you have too much air during the combustion, then probably you have a lack quality of combustion. Probably you will have the NOx, because the NOx can be produced in a very high temperature of combustion and can be reduced by the lack of air. So the excess air ratio is in a certain range of value. So you can check again in the last module about the combustion calculation. So the next one, we have to calculate the fuel mass flow for the combustion, and the next task, requirement of air and mass flow of the dry air. And the F, similar actually with E task, but F is for the volume rate, the volume flow of dry air. And the last task, we need to calculate the steam mass flow. Okay, so in this task, we have the question or the problems with the steam boiler, with the fuel of anthracite. This is a type of coal, black coal. And based on the elementary analysis, you have a certain composition of the fuel. You have the carbon components 86.2%, the sulfur 1.6%, nitrogen 1.3%, the water 2%, hydrogen 2.5%, oxygen 2.4%, and ash 4%. And then Based on the exhaust gas analyzer, based on the oxygen content analyzer, you have the oxygen content in the exhaust gas 2.3%, and then the firing power 2100 megawatts, the firing efficiency 0.96. The firing efficiency means the efficiency during the combustion process, during the firing process. Yeah. So it is not exactly as a boiler efficiency. Yeah. But this is merely about the process of combustion. Yeah. From the mixing of the air and the fuel. But in the boiler efficiency means the ratio between the evaporation rate to the fuel combustion process. Yeah? The added energy, the input energy from the fuel combustion. Yeah? So the boiler efficiency mostly in the context of the output of the steam rate compared to the input energy from the fuel combustion process. But in the firing efficiency itself, talking about the fuel process itself between the mixing of fuel and air, and the type of firing methods. Yeah. So in the below is the boiler efficiency. You have 0.87. Yeah. And the feed water temperature 180 degrees of Celsius. The steam pressure. I need to make a revision or correct this one. The steam pressure is not 225 but 22.5 bar. Yeah. And then the steam temperature 550 degrees Celsius. Yeah. So yeah, I need to delete this steam temperature. So in this task, we assume that the process of steaming or evaporation, it will produce a saturation steam, not superheated steam. So I assume that the steam still in saturation. Yeah. So if you had the steam temperature is 550 degrees Celsius and steam pressure 225 bar, it should be in the form of superheated vapor or superheated steam. So it is not matched with the requirement of condition. Yeah. So I just need the condition of steam pressure here is 22.5 bars. And the dry air condition, the pressure in the ambient pressure, the temperature is 0 degrees Celsius and the density 1.293 kilogram per cubic meter. Okay, so for the first task, we need to calculate the required minimum air. So based on the module of combustion calculation, there are two methods. Yeah. So you can use the first method of stoichiometric combustion calculation. Yeah. So stoichiometric is the chemical reaction, as I explained before in the last module. So from the stoichiometric, it means you have a balance of chemical reaction. Yeah. So you have in the last module, you can make a certain balance chemical reaction between hydrogen and oxygen, and then you produce H2O, for example. And maybe from the sulfur with the oxygen, then you have sulfur dioxide or sulfur, yes, SO2 or SO3, yeah, or maybe between the nitrogen and oxygen, then you have NO2 or NO3. Yeah, then you have a stoichiometric or balanced chemical reaction. So you can use the first method here. This is the requirement of minimum air volume, yeah, in cubic meter of air per kilogram of fuel. But then you can convert it into a mass flow or the required mass of air by the multiplied with the density of the air. Yeah. So then you can calculate the mass air minimum. Yeah. And then the second method, you can use the Molière-Hennebeau. Yeah. Based on the Molière-Hennebeau, you can check in the last module. You can use this formula. Yeah. But maybe I need to correct this symbol first. So the minimum air mass, yeah, the minimum of air mass equal 6,159 kappa. Yeah, this is kappa, not K, but this is kappa and sigma. Yeah, times sigma in kilogram of air per kilogram of fuel. Yeah. So then you can calculate the kappa and sigma based on Molière-Hennebeau formulas. Yeah. So wait a moment, I will show you the okay. So can you see the slides? So you can use this formula based on kappa and sigma, and for sigma, yeah, because for the oxygen you can calculate based on this formula. Yeah, so you just put the percentage of the carbon composition, the carbon components here, and for the kappa is based on this value. Yeah, this is for kappa. So kappa itself as a function or is the accumulation of several constants. Yeah. So the new here you can calculate based on this formula, and then the zeta here based on this sulfur formula here, and for the sigma you can use for the oxygen formula. Yeah. Okay. So that is the second method for Molière-Hennebeau. So I get back to the OneNote. This one, yeah. So you can calculate all the constant required for the Molière-Hennebeau, and then you can calculate the minimum air mass, yeah, in kilogram of air per kilogram of fuel. The second task, we need to define the net calorific value. So based on the last module, you can use the basic formula, yeah, to calculate the calorific value. So you just put the percentage of carbon, hydrogen, sulfur, nitrogen minus the energy of oxygen minus the energy of water. Yeah.
Excuse me, sir.
Yeah.
May I ask a question?
Yes. Yes. Please.
For the Molière-Hennebeau method, the calculation of kappa, so we just input the values of the elementary analysis percentage, sir.
Yes.
Oh, all right.
Don't,
And then I
don't
have
put this one. Don't put this
okay.
34,800 or 93,800. Just put the percentage. Yeah? For example, the
Okay, sir.
carbon 86.2%. Just put it the 0.862, yeah, in the formula. Yeah?
All right, sir. And I have one more question. For
Yes.
the calculation of net calorific value, do we
Yes.
not include the ash content, sir?
The net caloric value, yeah? No,
Yes.
in the net caloric value, we don't need the ash content, yeah? Because the ash you just need to throw away. You don't need the energy. Especially in the net caloric value, we just lost the energy also from the ash. Yeah. So if you have the the condition like this one, you have a composition from the elementary analysis, you have A, this is of S 4%, then you don't need to input it, yeah, to include the S energy in the net calorific value.
Oh, all right, sir. And maybe one more question, sir.
Yes.
For the calorific value of hydrogen, isn't it supposed to be 115,750 kilojoule per kilogram, sir?
Yes, that is for the gross caloric value.
Oh, all right, sir. But
Yeah.
for the net, it is always
Yes.
93,800.
Usually you have a less value for the hydrogen energy.
All right, sir. Thank you very much.
Okay, you're welcome. Okay, so I continue a little bit more for excess ratio. The excess air ratio, you just use the lambda for oxygen method, yeah, and then you calculate the all required constant for kappa and sigma here also, and yeah, this is maybe you have already calculated in the previous A if you use the molar MB, and then you can use all the constant to calculate the lambda, yeah, and the D is the required mass flow. So for the combustions, you need to calculate the mass flow rate of the fuel. Yeah, this is the formula to define the energy from the combustion process. Yeah, you need the mass flow rate of the fuel, the calorific value, the net calorific value, and also the firing efficiency. And then because you have the known data for the power, yeah, this one, the firing power, then you calculate the mass flow rate of the fuel here, yeah. And then for the x-axis, I mean the air mass flow of the dry air, because you have calculated the minimum air, and also you have the value of lambda, the air excess ratio, because the lambda is the ratio between the required of air divided by the minimum of required air. Yeah. So then you can calculate the mass flow of the air. Yeah. It should be m dot. Yeah. It should be m dot. This is the mass flow. Yeah. The mass flow rate. Yeah. And F is the volume rate. Yeah. It should be also with dot. Then you just calculated divided the E value with the density. Yeah. And for G, for the steam mass flow rate, yeah, steam mass flow rate, you need to check in the properties table at the pressure of 22.5. Yeah. So we assume that the steam still in the saturated condition. Yeah. Not in the superheated condition. Yeah. But after the superheater, then you have the superheated steam. Yeah. So you just need the condition at 22.5 bars in the properties table and check the value of the mixture. not the steam or not the liquid, but in the mixture, because in the rising tubes, you have a both mixture between liquid and steam, not already in the fully steam or gas. Yeah. So calculate the resultants between the steam dense enthalpy and the liquid enthalpy. Yeah. Then based on the known power, yeah, the power from the firing power, and then you just make an equal heat balance or energy balance from the firing power. Then you can calculate the required power for identifying or defining the mass flow rate of the steam based on the enthalpy here. Yeah. Okay, I think it's not so difficult, but you need to check the requirement of data and constants. Also check the properties table. Yeah. Okay. Any questions? So start from 8 o'clock. Now it's 8 o'clock. You can access the quiz one in the classroom. Yeah. So now you can open the quiz and you have 4 questions. Yeah, you have one for multiple choice and true and false, and 2 essays. Yeah. So put the screenshots of your calculations for the essay questions and upload it to the classroom before 9 o'clock. Okay? So you have a 1 hour time for complete your task, yeah, for the quiz. Any questions? So can you open the quiz now? So I believe it's already open. Yeah. Can you open the classroom and the quiz, ya, for at the meeting pertemuan 9, ya. Bisa ya?
Bisa, Pak.
Oke, mudah-mudahan